can scratch different various materials with the tip and report some form of nanoscale machine. Three different groups actually, all in 1992, three independent research groups trying that. As far as I can find, it's first of all useful as a group in Germany, making single electron transistor with a typical effect. So I've not found something yet for that in terms of application of technology. And then it's around 2005-2007 that the manufacturing community, perhaps the more conventional manufacturing community, tried to investigate the potential of this process from a more manufacturing point of view. So this is when a publication from a very active group in HIT, the Harvard Institute of Technology in China. So that was when Professor Yang Dayan was a PhD student at the time. Some work from Steve Capo at the UYUC. They had a micro machining setup, and they simply replaced the spindle by the head of an AFM to investigate the process. That's when I started at Cardiff trying to use our instrument to make a replication mold. And then Carnegie Mellon University, Professor Ozongala of Iraq, and with his PhD students, Arda developed and coined the so-called nano-milling process. They didn't really use an AFM because they did a system from scratch, but ultimately the tool was an AFM probe in this paper. And then this is work from Northern State University, as well as Simon Park in Calgary, trying to enhance the process by adding piezoelectric actuators. So with a view to generate vibrations between the tip and the workpiece, notably to reduce the tip weight. And some further work from Harvard Institute of Technology. This is just a selection. I mean, Professor Gagner was a PhD from Professor Yan, and they have done quite a lot of work. And you can also shape tools if you use a focused ion beam. You can shape the FM probe to generate a certain size grooves. So in a nutshell, what we've tried to do at Cardiff is first of all to see if we could create replication molds. The AFM is not an instrument that you can use as a machine tool really, but we try to see if we can sort of automate the CAD process with an AFM, increasing process throughputs. By this I mean increasing the speed or the cutting speed between the probe and the workpiece material, as well as the cutting length, modeling the process using analytical techniques, for example to simulate the surface roughness, and more recently using numerical tools to predict forces. And Rahul this afternoon we touched on this during his presentation. And in terms of application, we work with a colleague from the School of Physics to see if we could cut nanowires, nanomagnetic wires for potential data storage application. And when I say cut, I don't mean cut in half the wire, but just cut the surface of a nanowire, or create a nanochannel on top of a nanowire to control the motion of magnetic domain modes. So this is really briefly how it started, showing that this was a Friday afternoon activity, trying to see if we could create nano-replication or replication mode with nanostructures. And then trying to increase the process throughput by setting up a roll-to-roll approach on an AFM to cut, on this occasion, PMMA feet over long distance. Trying to understand the deformation of the cantilever. And because we observed a phenomena where the cantilever, when you apply initially, you indent the material, the cantilever is a convex deformation, but if you cut it along a certain direction, then you observe a different dramatic change in the dimension of groove, because we found that the cantilever changed from convex to concave deformation under certain condition. This was a CAD automation, so the idea was to really develop a C++ program on this occasion, which could read, essentially, what we wanted to do is for the AFM to be able to read J-codes and drive the trajectory of the probe. So AFM systems, as far as I know, are not able to understand J-code, so we did a pretty simple post-processor so that it could make the link between without lifting the tip. Because any FM has some sort of lithography software associated with it, but it's quite difficult to automate the control. Here what we try to do is was a little bit like Samuel Park and the work at North Carolina University, try to increase the process throughput. He was setting up piezo actuators, so shear-based piezo actuator on this occasion, underneath the workpiece, so that we could generate rotational motion between the erratic motion between the tip and the workpiece, and in this way try and increase the cutting speed at the interaction between the tip and the workpiece. Once we did that, we realized we are working with open board. We need to supply quite a high voltage to increase the amplitude of displacement as well as frequency. So what we wanted to do is to try and understand how our piezoelectric actuator behaves when you supply higher or reasonably high electric field and frequency. And for this, we combine some models published by the Committee for Piezoelectric Actuation into one to try and predict the behavior of D15 coefficient in that case, because we work with shear. And then more recently, we joined forces with a colleague in civil engineering, Dr. Segara, who is an expert in smooth particle hydrodynamics, and we wanted to see if there was value in using smooth particle hydrodynamics to model the process, and now we'll talk about that a little more detail this afternoon. So I'm going to go quickly through that slide because Rahul will touch on that this afternoon. This is the SPH-based work. We also want to try and see if we can use smooth particle hydrodynamics to model DPL, which stands for dynamic plowing lithography. So that's when you use the AFM tip in tapping mode, but in tapping mode such that particularly with polymer material, every time the tip lands on the workpiece, you create a nano indent. Okay? And there is also quite a lot of good work from having sort of technology using this process. And we want to see if using SPH can have value in modeling this process, because SPH is quite good for impact type mechanical problems. So this is just a research in its infancy at the moment. This is an illustration of what we want to do with nanowires. So essentially, when you have a nanowires, you apply a magnetic field, you can have the orientation of a magnetic field in the nanowires in the right to left or left to right direction. So you can imagine this is like a binary information, 0 and 1. The thing is that if you have a perfect nanowires, and what we see here between the red and blue area is a domain wall. Okay, so it's important to control the motion of such domain walls if you want to store information in a nanowire. Under perfect condition, domain walls are free to move in a nanowire. However, what we do is we try and cut a nanogroove on top of the nanowire, and it's important not to cut the nanowire completely, but just nanogroove on the top, so that you reduce the cross-section of the nanowire. And what we observe is that both theoretically and experimentally, we can pin the nanowire at this reduced cross-section area. Of course, to unpin the nanowire and make the 0 and 1 information carry on traveling along the nanowire, we can increase the magnetic field. But what's important is that we check that nanogrooves could be used as pinning sites for the control motion of the nanogrooves. And we also want to do some further modeling of the process. So we started simply with using the Johnson-Cook model, but modify with the integration of strain gradient plasticity, and try to see if we can also enhance such models to have multiple physical-based constitutive model in such models. But here we use a finite element. I should mention that we use finite element in that case. So laser processing will start, and my colleague will carry on after that. But just to give you an idea, for the past 14 years, we started with some basic research where we tried laser machine pure methods, and then there was we took some interest in processing bulk metallic glasses, particularly zirconium-based bulk metallic glasses, because it's quite readily available commercially. So I'll show you a couple of things in terms of modifying the weightability and compatibility using laser processing on such type of metals. And laser cleaning, laser polishing, and laser microstructure surfaces for energy application are also areas of research which we focused on recently. So I will go quickly through this one because this was at the beginning where we try and relate thermal modeling to single pulse craters that we observed. This work was more recent, where we try and replicate effectively what the research community had done in terms of weightability modification on titanium materials normally, creating groove dimples and groove patterns, but this time on zirconium-based bulk metallic glasses. We started working with the PNG, which perhaps was the most famous 10 years ago, a Vitruvian one, because it was really commercially available and you could cast, you could work with a bulk workpiece of a few centimeters thickness. But on this occasion, we used Vitruvian 105, a cousin of Vitruvian 1, because Vitruvian 1 has beryllium, and we were looking at potential for implant applications. So we didn't want to work with workpiece which have beryllium. So we worked with Vitruvian 105, and the good thing with Vitruvian 105 is that it's documented good fatigue properties. Because for implants, we use a material which can have good fatigue properties, the cyclic loading, typically in human as human implants. What we observed was that the weightability behavior depended not only on the particular topography, but also the change in chemistry on the surface of the material. And it's a combination of both. So what we found on this occasion is that the dimple pattern became more hydrophobic, even though the surface originally was hydrophilic and we had increased this roughness, so we expected hydrophilicity, but we didn't. And this was due to the reduction, we think, of carbonyl and carboxyl bonds following laser processing on the surface. And while for the groove pattern we had an increased hydrophilicity, but we also noticed a reduction in the carbon bond, the polar carbon bond. But on this occasion we think the surface roughness was the dominant effect and drove the hydrophilic property. While here the increase in surface roughness, while it should have been beneficial for increased hydrophilicity, it wasn't, because we think that what drove the behavior on this occasion was the change in chemistry. So it's important to, we think, look at both chemistry and change the surface roughness to understand the weightability change of the surface. And this was a follow-up study where once we had these surfaces, we drew cells and observed that the groove patterns was, as expected, the most favorable for the growth of cells because it had the hydrophilicity. And this particular piece of work, we worked with a colleague at Bath University, Alexander Lentz, and we wanted to, what we observed is that when you use laser polishing on such surfaces, depending on the fluence delivered, we could observe a softening of the material, which is well documented, but also hardening on a very narrow processing window. Laser hardening on bulk metallic glasses have been observed on a few occasions, but always in the case of laser ablation, where we introduce crystalline precipitates in the material. On this occasion, through laser polishing, we could observe both, and the change in fluence did lead to hardening and softening. And so what we did with our focus and beam and Alexander Lentz at Bath University, we try and measure the residual stress. So when you cut a cylinder and you register an image, and through image processing you can see whether the cylinder shrinks or expands and compute the residual stress as a result. This is a technique that Alexander is using, and that was really quite interesting on this occasion. So I will go. I see the time is running, so I will keep going. What we want to do in the future. Okay, so we want to use, again, back to Smooth particle hydrodynamics, not in the case of mechanical machining here, but for laser processing, because we think it's going to be particularly suitable to the nature of the modeling technique. From our experience, nothing quite with finite element analysis for mechanical, for the modeling of mechanical machining, but for laser ablation due to the phase change, solid, liquid, gas, smooth particle hydrodynamics would be quite useful. And here what we did, we actually tried to replicate the work at Manchester University from the group of Rogers, colleagues at Manchester University. And so we try and carry on from this good work, and we want to apply it to laser polishing. And here what we do is we try and solve the heat equation, the Navier-Stokes equation, take into account of surface tension and the Marangoni effect to predict with smooth particle hydrodynamics laser polishing, what if you given an initial surface roughness. So that work is ongoing. This is a preliminary result, but I think this is where really we can make the best use of smooth particle hydrodynamics technique in laser processing. And a dream of mine, and I will finish that before passing on to my colleague Samuel, is when you laser process a bulk metallic glass, so this has an amorphous structure to start with. Would there be a way to predict based on a set of laser processing parameters whether you induce or not crystal nucleation and the generation of crystal precipitate, in other words, amorphous matrix? I think this is a very challenging goal, but before I retire, I hope I can try and make progress on it, and also with the CIRP community, because I think it would be very nice to be able to predict. Here is an amorphous metallic glass, an amorphous metal. If you use this set of laser processing parameters, you are going to keep the amorphous structure, or you are not. I don't know if you are not able to do that, as far as I know, but that would be quite nice to be able to achieve that. Okay, thank you, and I will ask Samuel to carry on then. Take questions at the end. Yes, we're going to give you a quick overview of different areas.